So one of the most basic questions we're asked as theoretical computer scientists is what are graphs good for? And by graph, I don't mean actual function graphs, such as we can see here, or any other data graphs, such as bar graphs. What I do mean is a collection of points, which we call nodes or vertices, and lines that connect them, that we call edges. These lines can be directed, they can be undirected, they can have a certain value upon them, or they can be without any value. And it's quite interesting to know that pretty much any real life problem can find a suitable model within the aspect of graph theory. For example, we have a map of an underground train stations, and we want to reach from one train station to another in the shortest way possible. Or we want to transmit data over the internet, and we have a map of routers. So we'll focus upon distance problems, which is finding the shortest way to reach from one vertex to another vertex, or from one vertex to multiple vertices, or from multiple vertices to another set of multiple vertices. And we want to find these distances in the shortest amount of time possible. Now, when I say the shortest amount of time, I don't mean actual seconds or time units like minutes. What I do mean is the smallest amount of basic actions that we'll need to perform. So if we have a graph with n vertices and m edges, we can find the distances from a single source to all the um, other vertices in pretty much m basic actions. However, if we will want to find the distances from any pair of vertices, this will take us n to the third. Now, n to the third might seem not too large, but when considering certain graphs, such as this graph, which is a representation of the city of Berlin, we can see that actually the number of vertices is so large that n to the third might be too much. So what do? We give up upon retrieving the exact distance. We retrieve a certain approximation of the distance. But when we do this, we reduce the runtime. Now, any pair of vertices needs to have a certain distance. So we have n to the square pairs, so n square, the optimal runtime would be n to the square basic actions. And we have several types of approximation. We have a purely multiplicative approximation, where the distance will be at most twice the actual distance, or at most 3 times. We have an additive approximation. Distance will be at most the real distance plus a certain error, or we have a certain mixture of both types. And this would help us to reduce the runtime. Instead of n to the third, we'd have n to 2.3 or n to 2.1 and so on. For example, here we have a small graph where the distance from A to B is simply a single edge AB with the weight of 1. However, the distance for A and E is a larger path, but the weight is still 4. So if we retrieve the distance here with a certain error of up to the heaviest edge, that would be an error of at most 2. But if we look at, for example, A to H, here retrieving the distance up to a certain error of the heaviest edge would be at most 10. So there are various approximations. Sometimes we would want it to be purely multiplicative. Sometimes we want an additive error. And our focus is upon certain versions of these approximations and what can we do in runtime, which is getting closer to n to the square, which is our optimal runtime. And that would be all.